It's my pleasure to welcome Professor Naveen Garg from IIT Delhi for the first scientific talk today, and he's going to tell us about locating charging and service stations.
Thank you. Thank you for the invitation. I think it's a great honor to be part of these celebrations. I wish IMSC the best. 60 years. I have a cough, and that's expected from people traveling from Delhi, right? So please bear with me when I. This work that I'm going to be talking about today is joint work with two students, Rajni and Dilpreet, and a colleague, Nilima. And I'll tell you a little bit about, this talk is going to be more about algorithms, right? That's the area I work in, and specifically about what are called approximation algorithms. I'll tell you a little bit about what the context is. One particular area of research within algorithms, a large area actually, operations research algorithms is facility location. And a very common setting, let's say, is the following, right? That you are given some clients and you are given some potential facility locations. So in this picture, your clients are these square boxes, and the locations where you can open facilities are these circles. And you're given a metric on these, right? So you're given some distances between these various facilities and these various clients. And now it depends upon what you want to do, right? So you could have many, many different problems, and these all fall into this class of facility location problems. So one problem that we'll be interested in this talk is what is called the K-supplier problem. Okay, and that is just the following, that you want to open some K facilities. I give you this number K. You want to open K facilities, and in such a manner such that you minimize the maximum distance of any client to the facilities that you opened. Okay, so think of these as, these clients are locations of people who, let's say, access a public distribution system, and you want to open some ration shops, right? And so what would be good places to open ration shops, given that you are allowed to open, let's say, only K ration shops, such that the maximum distance any client has to travel is as small as possible. Yeah. So in this example, if K were 2, that is, you had money only to open 2 such shops, then if you place them at those 2 orange spots, then you would incur a cost of 9. What does that mean? That means that the maximum distance any client would travel would be at most 9, and I believe this client will travel 3 and 4, 7 and 2, 9 to reach there. Everyone else will travel less than 9, right? So this may or may not be the optimum solution, but I think it is, but you can check. There is also another problem which is called the K-center problem. And I think of it as, you're given some points in a plane, and you want to find out where, once again, the same things, but you have no restriction on where you can place the points, right, where you can open your facilities. And then the objective is still the same. You want to open the K centers in such a manner such that the maximum distance any client has to travel to the nearest facility is as small as possible. So this is classic facility location. And we said, well, everyone is talking about charging and electric vehicles these days, so why not see if we can produce, we can look at some of those problems coming from that domain. And that's what this talk is about. So that's where the charging stations come from, and I'll come to that in a short while. So now, earlier, our clients for these points, right? So we said people, houses of people. Now suppose clients for paths. Okay. Let's create a story. So suppose, you follow a certain route from work to home every day, right? So that's the path you traverse. And now you have these path information for many, many users. And let's say you are a service provider. Let's say you have petrol pumps. You want to open some petrol stations. Okay. Now, how should you place these petrol stations so that ideally you would want to place the petrol stations in such a manner such that no one has to deviate from their path to access a petrol station, right? But suppose you did not have the money to set up so many petrol stations, then it would make sense to look at the objective of minimizing the maximum detour one would have to make. Yeah, and so with that objective, so this is the setting now. So you're given these source destination pairs. So I'm going to be using these colors. So red color, and I can't use the pointer, but that's okay. So, or I can just do it on this. Right. So the red, there is this red path, and there is a green path which goes like that, and there's a blue path which goes like that, and so on. Oh, sorry, this blue path went like that. So these are the various paths, and now question is, how should you place two petrol stations so that the maximum detour any client has to make is as little as possible. Okay? So, right. So if we were to open once again these petrol stations at these two places, the orange blobs, then note that the yellow path would not have to take any detour. The green path would not have to take any detour. The blue will not have to take any detour either. The blue path, I do not know if you can see those colors, but the blue path is going like that. So one of the petrol stations is on it. The purple will not have to take any detour. So the only path that needs a detour is the red path, because there is no petrol pump on the red path. Right? The red path is going like that. And so this guy will have to come here, go back here. So there's a detour of 3 units, or a total detour of 6 units to access a petrol pump. Question, Meena? Yeah. Oh, you can't see the cursor. Yeah, the laser pointer does not seem to be. Can you see the laser pointer? You can, okay. So the yellow path, this is the yellow path, right? No detour needed there. Green path, no detour needed because there is something there. Blue path is this one, right? So again, there is a petrol pump on the blue path. On the purple path also there is a petrol pump. It's only the red path which is sort of, which is without a petrol pump, and there is a detour needed, and the detour is 3 and 3, 6. So we can count it whichever way you want, only the distance or twice the distance, it doesn't matter. So we're counting it twice the distance, so the maximum detour needed is 6. So that's the question. How would you, so given these paths, right, how would you place these K facilities so that the maximum detour is as small as possible? So a natural question to ask is, there is so much literature available on facility location problems. Why not use some of those techniques to solve this, right? What's the challenge? And the challenge is actually in all of this work on facility location, you assume that you have a metric. And we are also assuming that there is a metric on the points, right? But here, so one other thing that gets used very often is this inequality, which says that, well, if I have clients I1, I2 and some facilities J1, J2, then by triangle inequality, it should be the case that the distance from I1 to J1 is less than the distance from I1 to J2 plus the distance from I2 to J2 plus the distance from I2 to J1, right? So this is just whatever, quadrilateral inequality, whatever you would like to call that, okay? Now note that, okay, so first you will have to define, you'll have to think of what is the distance of a client from a facility, right? Now client is a path. So what is the distance of a path from a point? A facility is a point. Well, it's obvious to, a natural definition would be, let's look at the nearest point on the path and let's define that as the distance. But when you do that, this inequality goes away, right? You can't say anymore, and this is a very simple example to show that here on the right. So you have two paths, I1 and I2, and I have two clients, J1 and J2. Sorry, I should have, okay, I think I interchanged the clients and the notation for clients. But nevertheless, you have two paths, I1 and I2, and two clients, J1 and J2. And J1 sits on I2, and J2 also sits on I2. And J2 also sits on I1. Okay? So the distance of J1 from I2, the distance of J2 from I2, the distance of I1 from J2, all of these are 0. because they sit on them. But the distance of J1 from I1 is non-zero, right? And so, most of the machinery that has been developed for facility location problems, goes out of the window. We can't use it anymore. And what we can do, so we were exploring this and to see what are the various things we can solve in this setting. And there's a very simple algorithm you can imagine. For trees, it's, most problems are very simple, and that's the case here as well. Again, so what is the metric now is a tree. I give you these clients. I give you the source destination pairs, and I give you the path. And I say, find the smallest number of, what's given k facilities that you can locate, what's the smallest detour? And we turn this around, we say, let's first guess the value of the detour, right, that you need to make. So suppose my guess is D. So with this value of detour, I'm going to, fairly obvious thing. So you would, let's run through the algorithm. You would find the least common ancestor of each of these source destination pairs. So those are your least common ancestors. And now you're going to take the one which is furthest away from the root. So that would be, so that would be this one here, right? This is the one which is furthest away from the root. And from here, you are going to go D units up. So that's 2 units, D is 2. So you're going to go 2 units up, and you're going to pick this facility. You're going to open a petrol pump here. Why? Well, this is definitely going to cover this, right? Because this is the least common ancestor, and you're going only 2 units up from here, right? And in some sense, you need something below this to cover this pair, right? And so you've sort of taken the furthest thing closer to the root, and you just repeat this. And one can argue that this works. So, so you will, once you've picked that, you will remove everything that it covers. Note that it covers both the blue and the green paths, right? Because it also, but it doesn't cover the red path, right? Because the red will have to take a detour of 3 to get there. So you remove blue and green. They go out of the picture. And now you repeat the same thing for red, for whatever is remaining, and you will end up picking 2. And if you had made the right choice for D, then this will give you the minimum number of facilities that you need to open. So what happens when the metrics are arbitrary? It's not a tree metric. So remember, just to recall, you have these paths, right? And you're given a number k, and you want to find out how to locate these facilities so that the maximum detour that any client has to take is minimized. So if L is the longest path, let's say in terms of the number of edges, right? If L is 1, then this problem is like the vertex cover problem, right? L is 1 means edges, so each client path is just an edge. And what is it that you want to do, right? So you're given a bunch of edges, and you want to find some vertices which cover all of these edges, right? Which hit one endpoint of each edge. And that's like vertex cover, right? So the problem of checking if there is a detour of size 0 is the same as checking if there is a vertex cover of size k. And so it's NP hard, right? Even for L equals 1. And what we can do is we can give an algorithm which returns a solution of value 3 times opt plus L. Very weird number, but tight, right? So you can't do anything better than this, provably. Assuming P not equal to P. So I'm not going to say it's not a very difficult algorithm. So I'll go on to the charging station business, because I did not get to that yet. So we think of this previous problem that I just talked about more as locating service stations, right, or gas stations. Now, another interesting problem in the same domain is the setting of a charging station, right? So now you have electric vehicles. And then every electric vehicle comes with a certain range, right? What is the distance it can travel on a full charge? Okay, so now we're thinking of, we're given these source destination pairs, right? I have an electric vehicle, I work at IMSC, I live in wherever, and I need to be able to go every day from home to work, right? And for now, I'm assuming I can take any path whatsoever. I just want to be able to reach home, right? And my vehicle has a certain charge, certain capacity, and I should be able to drive in such a manner such that I never run out of charge. So we are going to assume that we are given these source-destination pairs, and we are given a metric on the terminals, again distance metric, and we'll assume that there is a range of B kilometers that any car can travel, an electric vehicle can travel. And we want to open the charging station so that every car can reach its destination. And we will assume that when a car starts from its source, it starts with a full charge, right? Because if it's empty, then what do you do, and so on and on. So at night, everyone charges their car fully, and so next morning when they start, they can start with a full charge. And note here that the paths are not specified. We are only given the source destination pairs. So in particular, just as an example, look at the picture on the right. So if, let's say this is the source here. Okay, so let's say the source is the top red square, and that's the path I want to follow. Of course, here we are not given the paths, but suppose that was the path I wanted to follow. I had a range of 200 kilometers, then I need a charging station at the green place or earlier for me to be able to make this journey. And with just that one charging station, I would have made this journey. So if I had just one single path, of course, I can solve the problem. But now we have many sourcing paths. And I want to identify the smallest number of charging stations I need to be able to to be able to service all of these customers. Yeah, I'm making it sound like it's all very important and useful. It's not, right? It's all just fun. So, but these are interesting problems that we thought of from a facility location perspective. Okay, what does the optimum solution look like, right? So this is where, okay, so what I'm going to do is, so we'll have these, remember we have these source destination pairs, right? So we'll think of them as these square boxes. So the red and the red, that's the source and destination for a particular vehicle and so on and on. And now if you look at where the charging stations are placed, so suppose you computed the optimum solution, right? What does that solution look like? So I claim the following, right? So suppose you took this metric that you had and retained only, you kept an edge. So let's say you create a graph and you kept an edge between two vertices if the distance between them is less than b, which basically means you can go from one vertex to another. Okay? So we kept only such edges. Now the optimum solution is a set of vertices O. So the optimum solution would look like these vertices, these circles in the picture, right? This is what it will look like. Let's see why. So what property should this have? So this should be some kind of a connected subgraph. We'll assume it's a tree. And it should be such that in each connected component, so every pair appears in a connected component or the other, right? So if this is where the thing was opened at those places, then I claim that the blue guy can go to the blue guy, the blue vehicle can go from its source to its destination. How would it traverse? It will start from there, it will go there. There's a charging station opened here, so on. And each of these edges of length less than b, so it will follow that and reach there. Long path, but it will do that. It can do that. And so our problem now is the following. I give you, so what is it that we want to do? We want to compute something like what's called a Steiner forest, right? I give you these pairs. I want to compute a subgraph which has the smallest number of nodes in it, because that's the number of charging stations I need. And in every connected component of that subgraph that I compute, every pair should appear in one of the connected components. So that's a Steiner forest problem. And a small technical point These are not just Steiner forests, these are what are called full Steiner forests, right? A terminal cannot be an internal node here, right? So imagine, so what's a terminal? A terminal is the home of some person, right? Now, if that's an internal node, what does that mean? That means that someone else comes to your house every morning to charge their car, right? That doesn't make sense. So these terminals have to be the leaves of whatever structure you build. And actually, it's an important technical consideration because this makes the problem much harder. So these are called full Steiner trees. So what we want to do is we want to compute full Steiner trees. And I'll tell you a little bit about this, and this might not make a lot of sense this slide might not make a lot of sense for people who do not know some of this stuff, but bear with me, I'll just quickly go over it. So if I have to compute Steiner forests with the minimum number of nodes in it, there is a log K approximation that is known, and it's possible to do that. But as I said, we want to compute Steiner forests which are full Steiner forests, and that becomes a much harder problem. It's equivalent to what's called the group Steiner tree problem. Actually, group Steiner forest, node weighted, and nothing is known, right? Or the only algorithm known is some quasi-polynomial time algorithm, which has a polylog approximation. But let's skip that. Let me show you one algorithm for this in the next 5 minutes. And here what we are going to do, so we are saying that, it's very hard to solve this problem, or the best approximation we can think of is it'll take quasi-polynomial time and polylog. It's not very interesting. Let's do a little bit. Let's do things differently. Let's change the problem a little bit, right? It's a standard thing we do when we can't solve a problem. We change it, right? So what we are going to do now is we are going to increase the range of our vehicles, right? Almost cheating, but that's the best we can do. So what we are going to say is, my vehicle, I'm going to develop a solution where I am allowed to travel twice as much as the best solution, right? So I'm going to look at the best solution with range B and compare it to a solution that I develop with a range twice B, okay? Okay, how do I do this? So we'll walk you through this. So this was, let's say, the graph and the metric that was given to me and the pairs and all of that. So we said we said this earlier. We'll take a metric closure, which basically means we'll add all edges by computing the shortest path distances between the points, and then we will only retain those edges which have length less than or equal to b. Right? You understand why I'm insisting on edges of length less than or equal to b, because those are the only edges we can use. If an edge is very long, much larger than b, I cannot use that edge. Or even the optimum solution cannot use that edge. So I do that. I have chosen b as 4, and I took that earlier graph that I showed you. I took the metric closure, and I was left with these edges. Right? The dotted edges are those that I added because of the metric closure. Now I'm going to compute a Steiner forest in this, a node-weighted Steiner forest in this graph that I have. Okay? So a Steiner forest which has the smallest number of vertices. So let's say these are the dark edges that I get. So I'm going to now throw away all the other edges so that you can see it very clearly what we have. And now you see what the problem is, right? So here, and I hope I can, so here we have a vertex here, right? This red one here. So this is a Steiner forest. As you can see, there is a path between every pair of vertices, right? So I can go from here to here by following this path. Ignore the colors because the colors were coming from the earlier setting, right? But if these were the stations that were set up, 1, 2, 3, 4, 5, 6, and 7 charging stations that were set up, then I know that this edge is of length less than b, this edge is of length less than b, this is of length less than b, this is of length less than b, and so on, and I can go from here to here. Looks fine, except that we have this problem that this is not a full Steiner tree, right? So note that this might be someone's home, what I said earlier, right? And how can I put a charging station there? So we want to get around that problem, and so what we do is the standard idea is that if this is of length, so I short circuit. right? I add these edges, which are of length 2b now, okay? And I will then remove one of those edges. So I got now, as you can see, a full Steiner tree. Can always be done, right? So this is a full Steiner tree. None of the terminals are any internal nodes in this tree. So that's where the 2b comes from, right? We said we have a range of 2b. Why do we need this range of 2b? Because we want to say that you can travel from here to here. Actually, this edge has length, does not have length less than b. This edge plus this edge had a length less than b, and so this edge has a length at most 2b. Okay, so I am almost out of time, so I'm going to stop very soon. But we took this further, and I'm not going to show you the whole algorithm here. We took this further and we said, okay, can we get a constant approximation, right? So still we're getting only a log approximation. Can we get a constant approximation? And we can if we allow a range of 4 times b, right? And this is a bit weird, right? So you saw the reason for 2b. I do not have a simple argument for why 4 times b suddenly you can go from log to a constant. But it's interesting that, you know, if you increase your range of vehicles in this manner, you can get a constant approximation. And I have nice slides for it, but I don't have the time, so we'll skip that. Okay. Just to tease you a little bit, let me. So with that, that brings me to what else we did. So that's interesting, right? So you can set up these, and what value does it have? What meaning does it have? I'm not particularly sure. But you can, by increasing the range of these vehicles, get better and better approximations. So we also looked at, suppose, so here in this previous problem, I told you we were just specifying the source and the destination. But suppose I also tell you that, you have to follow this path, or the vehicle is following this path, right? Earlier, there was no path that was specified for the vehicle. It could take anywhere till it could get from the source to the destination. Now, it had to take a certain path, and, it was not allowed to take any detour. Then, again, it's hard to get a better than a log k approximation. And we can extend this to show that you cannot even get a log k by alpha approximation if you're allowed a range of alpha times b. So it's a minor result, not a very great thing. So in this particular, so why am I putting this slide? So here for this particular problem, it shows that, this earlier you saw that increasing the range suddenly leads to a significant improvement in approximation ratio. That doesn't seem to happen here. You increase the range by 2, your approximation ratio will reduce by a factor of 2, not a significant drop as we saw earlier from log n to just a constant. Okay, so I'm going to stop now. So what I've shown you is how to, to this new set of problems that we sort of stumbled upon, locating these charging stations. We do not know of a lot of prior work on this. Much of the work has been done in the experimental community where they have some heuristics which they run to, but not in the TCS community. The unsatisfying part is that we are only able to obtain these pseudo approximation algorithms, right? That we have to increase the range of the vehicles to get any meaningful numbers. But getting true approximations seems like particularly hard in this setting. One other thing we've not considered is that, we said, I give you source destination, you could follow any path, but that means that you could also be taking a very, very long path, right, to get to your destination. And so is there a way of, limiting the length of the path and still obtaining meaningful approximations? When you start doing that, you hit these, these bad bounds, right? Everything seems to be polylog, at least polylog, and not a constant approximation. So that's all. This was more, this was work we did, during the pandemic, and somehow with the general, gloom around, the kind of results that we came up with were also not very pleasing or happy. But nevertheless, I thought I should talk about it a little bit to see if there are some fresh ideas I can get on, how one could look at different ways of addressing this problem, or whether there are variants of this problem one could come up with which would make interesting topics for research or discussion. Thank you.
Thanks a lot, Professor Garg, and thanks for keeping time. Please wait, we have a token of appreciation.
Okay. Thank you.